Hi students, this is AJ sir. Let's study electromagnet and its uses. 9th standard ICSE Physics chapter 10b. The definition: an electromagnet is a temporary strong magnet made from a piece of soft iron. When current flows in the coil wound around it, it is an artificial magnet. So some keywords here. First of all, it's temporary, which means the moment electricity stops flowing through the wire, it will no longer act like a magnet. And that is why we use soft iron as the core. If we use steel as the core, it tends to be a permanent magnet, or rather a long-lasting magnet, which means even after the electricity is switched off, it will continue to behave like a magnet if the core was made of steel. But soft iron does not become a permanent magnet. So then it is called an electromagnet. And remember, the current flows through the coil wound around it. The current doesn't flow through the soft iron bar. It only flows through the wire. And the wire is insulated, of course, with a plastic coating or any other such coating. That is why the current doesn't short circuit or flow through the iron bar. This electromagnet can be of two shapes: I shape or U shape. Now, this is how an I-shaped electromagnet is constructed. This diagram is double ticked, which means you need to practice it. We need not know the theory of how it is constructed. We can simply understand it with the help of the diagram. Look at the various parts of the circuit. We have a battery, which is multiple cells, one after the other. We have the key, which is closed. We have a rheostat for variable resistance, which means we can change the amount of current flowing through the wire by changing the resistance. And as you can guess, more the current flowing through the wire, stronger will be this electromagnet. That is one big advantage of electromagnets. We can control how strong it is. The ammeter tells us how much current is flowing through the electromagnet. The arrows show the direction of the current. You can see the current always flows from positive terminal to the negative terminal. Now, how can we determine which of the two ends, P or Q, will be the south pole and which one will be the north pole? Well, there is a trick to find out which is the north pole. If you look at this coil from the right hand view, and if you see that the current is moving in the anti-clockwise direction, then it is the north pole. Let me give you an example. Now, this is the electromagnet. Let me look at it from this point of view. Imagine that it was a three-dimensional electromagnet and I am looking at the end Q. So when I look from this point of view, imagine that this is the last coil of the wire. So how is the current flowing? I can see that it is moving anti-clockwise. It is moving anti-clockwise if I see from the Q end. That is, the current is coming from behind and then going down in front. So that is an anti-clockwise movement. So that's how I know that Q will be the north pole. Similarly, if I look at from the P point of view, I can see again, look at the red arrow. It seems that the current is coming from behind and then coming down in front. So from this point of view, it is moving clockwise. It is moving clockwise, and whenever the current is moving clockwise, that end is the south pole. So that was the clock rule, with the help of which we can always identify which is the north pole and the south pole. Well, you don't have clock rule in the 9th standard syllabus. It is actually a part of 10th standard syllabus. So it was just some good to know information. But all you need to know is that here this is the north pole and this is the south pole. See, if we draw an anti-clockwise current, even the ends arrow seem to be anti-clockwise. And look at the S arrows. It is clockwise. So that's how you can remember anti-clockwise is north pole and clockwise is south pole. Another hint is anti has an N, A-N-T-I, so N, so that is the north pole. One use of this eye-shaped electromagnet is that it is used in a relay. So you have to remember this. A relay is a switching device to switch on and off some other machine. The next type of electromagnet is a horseshoe electromagnet. The components are same. We have a key, a battery, a rheostat and an ammeter, and we have a soft iron core with a wire wound around it. So the current is moving in a particular direction in arm P, and then in arm Q that current is seems to be flowing in a different direction in the diagram. So it's very important that the arrows are shown exactly as it is seen here. They should be opposite to each other. Of course, the current is flowing from the positive terminal to the negative terminal finally. But in arm P, if we look at it from this view, we would notice it is going to the right from top, then it is going down to the left, and again coming on top and down to the left. So this is a clockwise movement of the current. That is why this acts like a south pole. And here the current moves to the left on top, then goes down to the right, on top to the left, down to the right. So this is an anti-clockwise movement of the current, and so this end behaves like the north pole. So you don't have to know the clock rule in 9th standard, but if you do, it will help you to prevent the confusion between which of the positions should get the north pole and which one the south pole. Now the electromagnets, horseshoe electromagnets, are used in DC motor and AC generator, etc. DC means direct current, where the direction of current and magnitude as well is constant. For example, the current from the battery. AC current, AC means alternating current. That means the direction and the magnitude of the current keeps fluctuating. For example, the current we get at our households. The functioning of DC motor and AC generator will be explained in detail in 10th standard. Now note that in this diagram we have used a DC source of current, that is a battery. But what if we would have connected this circuit to our household socket? Then it would have received an alternating current. That is also okay for the functioning of electromagnets. But then since the direction of current keeps changing, even the polarity will keep changing. So in this diagram the arrow is this way, so this is the south pole. In a fraction of a second, if the direction of current changes, then this will become the south pole and this will become the north pole. So this is actually another advantage of electromagnets, because we can change the polarity of the magnet by changing the direction of the current. And since the frequency of the alternating current in our households is 50 Hertz, that is 50 cycles per second, even the polarity would now change 50 times per second. Now if I ask you to think of ways in which you can increase the strength of an electromagnet, that is of the magnetic field, can you guess how we can do that? Pause the video and think about it. Okay, let's resume. Well, I'm sure you've guessed that we can increase the strength of the magnetic field by increasing the amount of current. I had already mentioned that earlier. But there is one more way. We can increase the number of turns of winding in the solenoid. Solenoid means the coil. So you can see here in the diagram, we have so many windings. 1, 2, 3, 4, 5, 6 windings of the solenoid or the coil. If we would have increased the number of windings, then it would be an even stronger electromagnet. So that is yet another advantage of an electromagnet. We can change the strength of the electromagnet by either changing the amount of current flowing or by changing the number of windings. And that is why we can have super powerful electromagnets as well. Let's compare electromagnet to a permanent magnet. Now I've cancelled these paragraphs and even the advantages because all of this is covered in this very important differentiate table. There are 6 points. The first difference between electromagnet and permanent magnet is that this is made up of soft iron and this is made up of steel. So that's why even if we switch off the current, the magnetic field will stay for a permanent magnet, but electromagnets are temporary. The last 4 points are advantages of electromagnet. The magnetic field strength can be changed. Here it can't be. The magnetic fields can be very strong. Here it can't be very strong. The polarity, that is the North Pole and South Pole positions, can be reversed, but not here. And electromagnet can be demagnetized very easily. Just switch off the current. Switch off the current with the help of the key or the switch. Permanent magnets cannot be demagnetized easily. You'll have to heat it or hammer it or wait for a very long time for it to get demagnetized. Next topic is uses of electromagnets in our daily life. Well, it is used for lifting and transporting heavy iron scrap. It is used for separating iron pieces from debris and ores. It is also useful for removing pieces of iron from wounds or from the eye. And it is used in several electrical devices. All modern day devices work on the principle of electromagnetism, including electric motors, microphones, loudspeakers, etc. Let's study the working of one such device, the electric bell. Again, this diagram is double ticked, so you'll have to practice it. But I will show a simpler diagram. We need to remember the names of all the components and the functions of each of them. I will explain the working as well. You need not learn the working. It is just to be read. Also remember that this electric bell is very different from the electronic bell in the modern households. The electric bell is typically used in schools, especially with the old ringing system. After the end of each lecture or after the end of the day, it would just ring and students would be delighted at the end of the day. The electronic bell, on the other hand, in our modern households may even have a song or some music playing or a ding dong bell. That is totally different from what we are going to study now. So this is the highly simplified version of the diagram which you can draw. This is the gong. It is fixed. This is a hammer. This is the armature, which is made up of iron. This is a metallic strip. This is called the screw. These are the wires, connecting wires. This is a horseshoe shaped soft iron core, which will behave like an electromagnet. And these are the windings of the wire around it. So when you turn on the switch, current starts flowing from positive terminal to the negative terminal. When the current starts flowing, this will become an electromagnet. So it will attract this armature towards itself. So it will move towards itself like this. it is fixed at this position, so the top part will be attracted towards it. Now when it moves ahead, the hammer will hit the gong. But notice that if it moves ahead, then its contact with this screw will be broken. Right now in this position, it is in contact with the screw. So the circuit is complete. The current will flow through it. But if it moves ahead, then there is a gap between this armature and this screw. So the circuit is broken and the current will stop flowing. And if the current stops flowing, it will no longer act like an electromagnet. So it will no longer attract this armature. So due to a spring-like action, the armature will go back to its original position out here. But if it goes back to the original position, it will once again come in contact with this screw. So again the circuit is completed. Current will now flow through this circuit. This will become an electromagnet. It will attract the armature and the armature will come ahead, and again the hammer will hit the gong. So this continuous making and breaking of the circuit, the magnetization and demagnetization of the electromagnet, means the hammer will keep hitting the gong and go back. This is how the electric bell works. Now, one very crucial aspect of drawing the diagram are the arrows of the current. Make sure you draw it exactly as it is shown here. Especially in the windings, note how the winding came from behind and going down from the top, going up at the bottom, going down from the top, and so on. Whereas here, it is the opposite, going up at top and then down at the bottom. Up from the top and down at the bottom. So look at the arrows. Here the arrows are downwards and here the arrows are upwards. Only then will it work. Now can you guess from the clock rule which of these poles will be the north pole and which one will be the south pole? Pause the video and think about it. Well, if you see from this end, okay, you will notice that the current here is moving clockwise. So this will be the south pole. And here the current is actually moving anti-clockwise. It's going anti-clockwise. So this will be the north pole. That's not important in this diagram because it actually doesn't matter which of these is the north pole or the south pole. The electric bell will function either way. This also means that instead of a DC source of current like batteries, if we were to connect it to an AC source of current like your household sockets, where the current's direction keeps changing, where the polarity of the magnets keeps changing, it won't affect the working. Because no matter what is the polarity, it will attract the armature and the hammer will hit the gong. That means this electric bell will work even on AC current. So that's what is explained in the note. Hi students, if you found this video useful, press the like button. Also to enroll for my online lectures or online test series, email me or message me on Instagram. Check the description for more information.